I don't talk about the software. For a simple reason. There are 2,000, if you consider the software available for a specific task, you have tons of different tools. For sequence alignment, more or less remain the same software such as Clastal, Fastal, so other. But if you go, for instance, to find microRNA target, you have 10 to 100 different software. To make a survey and to make a benchmark of different tools is a, let me say, NP-complete problem because you've lost your life. Because any paper said my tools is the best of the world, but it's the best of the world on my training set, not in your training set. In a previous lesson, I talked about the standard. We don't have a standard to check the quality of the bioinformatics software. So I'm starting to work in bioinformatics more or less 25 years ago. No standard in the initial phase, no standard in the middle, no standard now. The problem is for you, because the problem of lack of standard is the problem of reliability of what you extract from the data. The only standard that now exists is a context for protein structure prediction that is called CASP, Critical Assessment of Structural Protein Structure. This consortium has decided to use a specific, well-defined data set to test the performance of different software. It's the only case of standard. If one of you find a similar thing for genome sequences or for microarray sequences of what you want, please inform me. I pay to him a dinner because I never found. There are the standard for registration. There are the standard for database creation. There are specific language to generate structured database for microarray. But the idea to standardize microarray or to make the same thing on functional genomics, if you have some idea, I am open to hear. But at the moment, for my experience, there is not. The other question is nucleic acid structure. Nucleic acid structure prediction is a very complicated situation. When you use DNA structure in the database, the majority of the sequence and structure contain GCG-rich domain. Why? Because are more compact and it is more easy to be crystallized. But if I want to study a rich region, you have a lot of problems. If you want to analyze high content of weak nucleotide or synthetic, designed ad hoc, then it's not natural, or otherwise are strongly modified in a way to stabilize the structure. But it's not the true the true structure of the protein, the nucleic acid. This is the big problem. For RNA, it's worse. For RNA, for instance, you told 90% of a large amount of software are based on direct cyclic graph system to build the 3D structure. You have a graph, but when you attempt to create a 3D structure starting from a graph, and then you compare the system is similar to protein. You have templates on which the software assembles the model. When you check the quality and the control the structure between template and the resulting model, you have some problems. Then there are, in the structural part, in the structural genomics, mainly on nucleic acids, there are many challenges in front of you. And the other thing is, for instance, ribozyme. I want to engineerize a ribozyme. I saw that some guys working with Professor Pasandani working on ribozyme. Then this ribozyme can be engineerized for other tools. But in which way it's possible to modify a nucleotide using a system such as Chimera is not easy. And it's not possible, and you can modify the primary sequence, create a model, and then submit the model. But we are in the same situation, previous situation. The model is generated by graph. The graph originated is linked to a thermodynamic analysis. The resulting conformation is the resulting structure is the optimal energy structure. This is the last notation. Thanks a lot.